In Episode 3, we related general relativity to the quantum vacuum utilizing three key equations. That is, the refractive index of space-time, the quantum vacuum amplitude spectrum and the quantum vacuum frequency spectrum. This facilitates the concept of space-time engineering utilizing the polarizable vacuum approach to general relativity, by employing the superposition of transverse electromagnetic plane waves, which are quantized over the Fourier domain. However, an important property of the quantum vacuum remains unresolved. In Episode 3, we derived the lower frequency limit of the quantum vacuum in the presence of matter, but what about the upper frequency limit? How can we calculate that? In this episode, we derive a solution for the upper frequency limit of the quantum vacuum, when polarized by the presence of matter. This polarization effect transforms the quantum vacuum into the polarizable vacuum model of general relativity. Therefore, by the end of this presentation, we will have clearly and precisely defined the spectral limits of the quantum vacuum, as well as having unified general relativity with quantum mechanics. So, let's get started. Before we derive the spectral limits of the quantum vacuum, we should understand that the solution for the upper frequency limit was a vintage, 92 years in the making. It started in 1914 with Buckingham pi theory. Soon after, in 1916, general relativity surfaced. Einstein's application of the equivalence principle begs the question as to the possibility of him taking the idea from Buckingham. A central tenet in Buckingham pi theory is the principle of dimensional equivalence, in tandem with the principles of dynamic, kinematic and geometric similarity. Whether or not Einstein borrowed from Buckingham without the appropriate citation is an academic question. Nevertheless, the timing is undoubtedly suspicious. It is also worthwhile emphasizing that the idea of Einstein being a genius in developing general relativity in isolation, is somewhat of a romantic notion, far from the truth. Without the mathematics underpinning general relativity is a conversation and nothing more. The real power and elegance of general relativity rests with the mathematics involved. It took Einstein 10 years and access to professional mathematicians to flesh it all out. So, Einstein was never alone in the lifeboat. Moreover, historians are now calling into question the possibly unrecognized intellectual contributions made by his first wife. Additionally, if we critique Einstein's original general relativity manuscript, it's obvious that it would fail the referee process of the modern era. At the very least, it's 54 pages long and would be considered too lengthy to publish nowadays. So, the fact that Einstein was published at all, is a product of the times he lived in. The next significant period was from 1994 to 2006. The 1994 research executed by Hayes, Rueda and Puthoff was groundbreaking, and in our opinion, worthy of significantly more attention than it has received to date. In addition, Puthoff's 2002 research article expressing the complexity of general relativity at a point in the space-time manifold as a single value of refractive index, based upon an optical interpretation of geodesic motion, was equally revolutionary. The research article published by Storti and Desiato in 2006, was the final piece of the puzzle. It combined the single-point characteristics of the quantum vacuum with Newtonian gravity, utilizing Buckingham pi theory, which we covered in Episode 2. In Episode 3, we built on previous work by relating general relativity to the quantum vacuum and converting the experimental relationship functions of Episode 1, to a value of polarizable vacuum refractive index. We then introduced the concept of a unit harmonic operator, which enabled us to calculate the lower frequency limit of the quantum vacuum. In this episode, we calculate the upper frequency limit of the quantum vacuum, which completes the picture. So, as you can see, the story began in 1914 with Edgar Buckingham and ends with Storti and Desiato in 2006. The story containing Episode 2, 3 and 4 material is taken from a 2011 summary published by Storti, titled, The Extraterrestrial Casimir Effect. Let's now move forward. In Episode 3, we learned that the presence of matter polarizes the quantum vacuum, which forcibly upshifts the lower frequency limit of the quantum vacuum from 0 Hz to 36 mHz, at the surface of the Earth. A similar process occurs with the upper frequency limit, but in reverse. the presence of matter downshifts the upper frequency limit from infinity, in perfectly flat space-time, to some other value in curved space-time. This episode, episode 4, focuses on calculating the upper frequency limit I just mentioned. However, to best achieve this, we need to understand certain characteristics associated with the nth harmonic mode of a Fourier distribution. We need to do this because a Fourier series extends to infinity, and for the complete representation of a constant function utilizing Fourier harmonics, the nth harmonic mode equals infinity. But therein lies a problem. That is, we need to be able to retain the infinite harmonic mode boundary, and simultaneously solve a real-world problem. So, how can we achieve this? We shall start by utilizing the unit harmonic operator in the illustration shown. We see that the graphical representation of the 11th harmonic mode is actually the sum of harmonic modes 1 to 11. It is important to understand that any specific harmonic mode includes a summation of all harmonic modes before it. In other words, the 11th harmonic mode is not unique or special, it is merely the partial sum of an infinitely broad series. The next thing we need to do is understand what is mathematically happening at the midpoint of the period. The reason that the midpoint is significant is because it contains the characteristics of a single harmonic frequency mode. We shall exploit this characteristic later on, but for now, we'll focus on what's happening at the graphical midpoint. By zooming in on the midpoint, we see that a peak-to-trough difference exists between the 9th and 11th harmonic modes. We see that the blue curve, which represents the summation of the first 9 harmonic modes, peaks at the graphical midpoint. However, we see that the red curve, which represents the summation of the first 11 harmonic modes, troughs at the same location. Let's see if a similar situation occurs at a higher harmonic. In this next illustration, we see a comparison between the 19th and 21st harmonic modes. By examining the graphical midpoint, as before, we see that the peak-to-trough situation has been reversed. In this harmonic solution, the red curve peaks whilst the blue curve troughs. This flip-flop mathematical behavior emphasizes the futility of choosing a practical value of n, that is, the futility of not knowing when to stop summing. So, is there a workaround? Fortunately yes, a workaround exists. By focusing on the difference between the mean values of the theta functions 1 and 2, over one period as shown, we've turned the problem on its head. That is, instead of summing to n equals infinity, we're summing until the difference between the mean values of the theta functions 1 and 2 tend to 0 over one period. Tending to 0 is a far more convenient limit, rather than tending to infinity. By targeting 0, we're targeting a practical definition of infinity. For example, we are able, if we wish, to target an extremely small margin of error. We shall show this to be a very important feature of our solution to the spectral frequency limit going forward. So please keep this in mind. Utilizing the conclusions derived in the previous slide, we may converge to a harmonic solution in 3 simple steps. The equation appearing now is a reformulation of the spectral energy density equation stated by Hayes, Rueda and Puthoff in 1994, expressed here in polarizable vacuum notation. The reformulation shown expresses the energy density per unit frequency, applied as Hertz. Thus, step 1 involves integrating this equation over the frequency domain, yielding a value of energy density. In step 2, we let the value of frequency appearing in step 1 to be equal to the fundamental harmonic frequency derived in episode 3. By doing this, we have determined the energy density of the fundamental harmonic frequency in any gravitational acceleration field. This means that the harmonic cutoff frequency, that is, the upper spectral frequency limit, will be a harmonic multiple of the fundamental frequency. Now we have a highly convenient approach. In step 3, we leverage off the conclusions derived in the previous slide, and are able to simply write down an equation for energy density at the nth harmonic mode. As we have previously determined, the difference between a single change in frequency mode tends to 0, as the value of the nth harmonic tends to infinity, thereby yielding a converging solution. Going forward, we shall solve for the upper spectral frequency limit, utilizing this equation. Utilizing the approach defined on the preceding slide, we may derive the upper spectral frequency limit in 4 actions. First, we equilibrate the mass-energy density, in this case, a spherical body, to the energy density at the nth harmonic mode, as shown. The process forward from here involves some complicated algebraic manipulation and mathematical gymnastics. The complete mathematical process is outlined in detail in Appendix B of the research article titled, The Extraterrestrial Casimir Effect. Please refer to this document as required. For now, we will skip over the detailed formulation and declare the important outputs only. The equilibration process produces two important declarations. That is, the harmonic cutoff function and mode. The harmonic cutoff function is simply a mathematical tool facilitating the computation of the harmonic cutoff mode. However, the harmonic cutoff mode denotes the upper spectral limit. That is, the harmonic cutoff mode represents the highest and final harmonic mode of the polarized quantum vacuum, at position r, induced by gravitational mass m. Thus, additional harmonic modes do not exist beyond this boundary. In other words, the presence of matter has pushed the quantum vacuum uphill by polarizing it, acting to downshift the spectral limit from infinity to the value calculated. Once we have determined the harmonic cutoff mode, it is a very simple matter of multiplying it by the fundamental harmonic frequency, in order to calculate the upper limit of the polarized quantum vacuum spectrum. We term this, the harmonic cutoff frequency. Once obtained, we have achieved our objective and are able to clearly and completely define the frequency distribution in a gravitationally polarized form of the quantum vacuum. This means that, with this information, we are very close to establishing a rigorous quantization of general relativity. So, let's inspect what we've achieved so far. That is, what does the complete solution consist of? Well, in episode 3, we established the quantum vacuum amplitude spectrum, the quantum vacuum frequency spectrum, the refractive index of the polarizable vacuum and the fundamental quantum vacuum frequency. In this episode, we established the harmonic cutoff function, the harmonic cutoff mode and the harmonic cutoff frequency. With both sets of derivation in place, we have a complete solution. We now have the ability to completely define all relevant and important aspects of the polarized form of the quantum vacuum, at position r, induced by gravitational mass m. Our cubic frequency distribution demonstrates that spectral energy density increases with gravitational intensity. In this illustration, we have broken the cubic frequency distribution into 4 regions. Region A relates to cosmology, whereby space-time geometry has been experimentally confirmed to be flat. Region B relates to the astrophysical scale of cubic frequency distribution, whereby space-time geometry has been experimentally confirmed by general relativity to be curved. Region C relates to the particle physics scale of cubic frequency distribution, whereby space-time geometry is usefully approximated as being flat. Lastly, in Region D, at the theoretical Planck scale of cubic frequency distribution, space-time geometry is assumed by the scientific community to be curved. The dominant gravitational model associated with each region refers to the state of the quantum vacuum. In Region A, the quantum vacuum exists at its minimum energy condition. The name given to the quantum vacuum in this condition is zero-point field. In regions B, C and D, the quantum vacuum is polarized by the presence of matter and the quantum vacuum is termed polarizable vacuum. If we now look at the harmonic mode distribution, we see that it increases as spectral energy density decreases. Region E, representing the Planck scale, indicates that with sufficiently large mass, the number of harmonic modes equals unity. The important takeaway from this illustration is that the number of possible harmonic modes in the quantum vacuum tends to infinity as the quantum vacuum approaches its zero-point field ground state. Conversely, as gravitational intensity, that is, space-time curvature, increases, the quantum vacuum harmonic mode population decreases.